In section 5.3, we're going to take a look at differentiation now again, and we're going to be taking derivatives of inverse functions. Okay, this first slide is dedicated to reviewing all the things we need to know about inverses so we can talk about the derivatives of an inverse function. So let's suppose we have a function f graphed here, and I'm indicating that there's a point on this graph a comma b. If we wanted to graph the inverse of this function, you're going to have to recall that an inverse graph is a reflection about the line y equals x. So if you graph the line y equals x and reflect your graph about that line, that would give you what the inverse graph would look like. And just to be very certain that we're not misinterpreting this notation, this is not a power. When we write f to the -1 power, so to speak, that's indicating an inverse function. So really we shouldn't refer to it as a power, it's more like a superscript. So be very careful with that. The other thing we got to point out is that point a comma b on the original function's graph is now the point b comma a on the inverse function graph. One other thing we need to know about an inverse is how do we prove in a way that we have two functions that are inverses of each other. Well, if a function g is going to be an inverse of a function f, then two things have to be true. If you take the g function and plug it into the f function and you get x, that is a good thing. If you take the f function and plug it into the g function and get x, that is another good thing, because if both of those are equal to x, that's how you know f and g are inverses of each other. So that's a very important thing, as some problems don't tell you functions are inverses. They might tell you these two things are true, and then you need to read between the lines in a manner of speaking and realize that they are inverses. The other thing, just to reiterate one more time, is this notation again is not f to the -1 power, it's a superscript, so to speak, and not a power. If you ever see that, we know that f is being indicated to be an inverse. The other thing we have to address concerning inverses is when do we have an inverse function? Just because you have a function doesn't mean it necessarily has an inverse. And the way we need to check, or the way we can check if a function has an inverse, is if your function is 1-to-1. So if you forgot this, there are two ways to check if a function is 1-to-1. The first way to check is using the horizontal line test if you have a visual of your graph. And you can see right here, this graph doesn't pass the horizontal line test since the graph touches a horizontal line more than once. And just, I guess, on top of that, realize that this is a parabola, so parabolas do not have an inverse. The other way we can check for a function having an inverse is to see if it's strictly monotonic on its entire domain. Now, that's probably some wording and vocabulary you've forgotten if you've maybe ever known it. So as either a quick review or just a way to quickly illustrate how simple this vocabulary word is, even though it sounds complicated. Strictly monotonic means that your function is always increasing or always decreasing. If it's always increasing, then of course, and I'll just kind of scribble a graph here, if it's always increasing, then of course it's going to always pass the horizontal line test. If your function is always decreasing, then it's still going to pass that horizontal line test. So again, just a fancy vocabulary word to illustrate something that we can see visually. One note to make is that if a function is not 1-to-1, then we can change its domain to make it 1-to-1. And usually that'll happen in trig functions, but even if you imagine using this parabola as an example, if we were to take this parabola and kind of erase, so to speak, the left side of it, in other words, if we restrict its domain, or change its domain just to this left side of the parabola, then it would pass the horizontal line test. So just a little note to make that if a function isn't one-to-one, we can change it a little bit and make it one-to-one by restricting its domain. Okay, so let's now talk about finding the derivative of an inverse function. So let's suppose we have our function f here, and we have the point a comma b. You can see I've drawn a tangent line at the point x equals a, because we're trying to start talking about derivatives here. And of course, we should all remember that a derivative is the representation of the slope of a tangent line. So I'm going to graph the inverse on a separate xy plane just so it doesn't get too messy. So if we take the inverse of f of x, which I'm going to call g is going to be the inverse of f, then that would mean the point on the inverse graph is b comma a. And of course, that has a tangent line as well at the point x equals b. So talking about our original function, we know that the derivative at point A has some slope. And again, this should make sense. F prime is a derivative, and a derivative is equal to slope. To relate that to the derivative of our inverse function at point B, you're going to have to recall that the slope of a reflected tangent line will be the reciprocal of the slope of the original tangent line. That is to say, if we wanted to find the derivative of g at point B, that would just be 1 over m. So as a quick example, if I told you the derivative at point A was equal to 3, then that would mean the derivative for the inverse function g at point B would be 1 over 3. So it's really that simple. If we can find the tangent slope for the original function, all we're going to have to do is take that slope and write it as a reciprocal. So the best way to do these problems is to kind of set up a little table here, and I'll have you guys do these and all the ones you attempt. We're just going to make this little table of information here to organize what we know, and then it makes getting these answers a little bit easier. So we're going to suppose that f is our original function, and when we take the inverse of it, it's going to give us g. We know that the point a comma b on the f function becomes the point b comma a on the g function. And if I know the derivative at a is equal to m, then we know the derivative for g at point b is equal to 1 over m. So the good news here is we can find the derivative of an inverse function without ever actually finding the equation for the inverse. And the reason is this: if we can just find the derivative for the original function, then we just have to take that slope of m and write it as a reciprocal for the inverse function. So these are actually very, very straightforward basic problems once you jump into them, once you realize that little fact. Okay, so let's take a look at a couple examples. We have two functions f and g that are differentiable. For all x values, they tell us that f of g of x is equal to x, and g of f of x is also equal to x. That piece of information right here is very important, because you'll notice nowhere in this problem does it mention that f and g are inverses. But this little piece of information is indicating that they are inverses. And again, refer back to the last slide to see that. They tell us that f of 3 is 8, f prime of 3 is 9, and I want to find two values, g of 8 and g prime of 8. So let's go ahead and set up our little table. We know they give us the point f of 3 equals 8. So we know it's going to be the point 3 comma 8 on our f function, which would mean on our g function, the point would be 8 comma 3. And we've already answered one of the two questions. They asked us to find g of 8. And you can see right here, we have the point 8 comma 3, which means g of 8 is equal to 3. To find g prime of 8, we're going to have to use the second piece of info they give us. They tell us that f prime of 3 is equal to 9. If we want to find g prime of 8, then that's just going to be the reciprocal of that slope, and that slope is 9. So 9 becomes 1 over 9. Okay, one more example here. We're going to let f be defined by the function f of x equals x cubed plus x. If the function g is the inverse of f, that's the notation for the inverse, that's superscript of -1, and g of 2 is equal to 1, what is the value of g prime of 2? So, as soon as we see that they're inverse functions, let's go ahead and set up this little table. So we don't have a point on our original function. We're going to have to kind of work in reverse here, so to speak. They give us, the value g of 2 equals 1. So we know our inverse function has the point 2, 1. If we kind of reverse that, so to speak, we know the point on the f function was 1, 2. So we're trying to find g prime of 2. We can't find g prime of 2 unless we go to the original function and find f prime of 1. If we find f prime of 1, once we have that value, we'll just find the reciprocal of it. And you'll notice these x values have to match. If it's 1 here, it's 1 here. If it's 2 here, it's 2 here. So we need to find f prime of 1 first. And luckily, that's nice and simple. The derivative of x cubed plus x is super simple. That's just 3x squared plus 1. And if we want to find f prime of 1, we'll just take 1 and plug that in. 3 times 1 squared plus 1 is 4. And of course, to find the slope for g at 2, which is an inverse function, we'll take that slope of 4 and write it as a reciprocal. And that gives us the value of the derivative for the inverse at 0.2.